Okay, welcome to the Union League Club Tech Group meeting for June 2020. Hope everyone's staying healthy. Updates on the clubhouse, we're open for phase 3. You must wear a mask, but you can pick up food in one cafe or in the carvery, and you can sit and work on in President's Hall or the library or the Crystal Room. So it's good that we can take advantage of the clubhouse again. Now onto the topic for today. I feel like science has been marginalized recently, and I feel like now more than ever we need ambassadors to help us appreciate topics that are difficult to understand. And I can't think of a better person to do that than Dr. Ted Lieu. His unique blend of skill in hard sciences, history, getting the big picture, in storytelling makes him the perfect person to teach us about science and what it brings for us. So Dr. Lieu received his PhD in physics at Harvard. He's worked at Princeton and Berkeley Lab. He's currently at Fermilab and also worked at Cornell, Stanford, and University of Chicago. And he's currently working on projects at CERN at the Large Hadron Collider. So very happy to have Ted back today to give a talk on atom smashing. Please give a warm Union League Club welcome to Dr. Ted Lieu.
Okay, thanks very much, Jeff, for inviting me back again. Last time it was last November that it was in person. This time it's going to be remote. And this is a very big topic. What I was going to talk about, as you can see, is physics and the atom smasher and the technology. So this is very broad, and I won't be able to get into too much details, but I'm hoping to give you a sense of the overall what happened in the past couple hundred years and where we are now and where we're going to. So that's I'm hoping achieving that goal towards the end of the talk. So just want to remind you that atom smasher is really it's a name which started really early days, but really what we're doing right now is we're colliding very fundamental particles, subatomic particles like protons, electrons. So atom smasher is an old name, but we do also smash atoms when we're doing heavy ion runs, like gold atoms was ionized or lead to lead atom smashing. I'll come back to those things later, but I just want to clear up the name. I still use atom smasher because that's what people remembered. So let me first start with a cartoon which my friend sent to me a year ago, which actually motivated me in some way to prepare a talk like this. It was about, along with antimatter and dark matter, we have recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. So this is actually pretty interesting because many people actually think, even among our own scientific community, some people sometimes arguing that what we do does how much, some of that is too far away from reality, especially people in the mathematics or in related to physics, superstring theories. But I will try to, I try to go back in history and really look at the whole history. And if you go back in a couple hundred years, you will see things in a somewhat different way. So that's what I'm hoping to do today. So I was started with a trip I made last year. Was very interesting. It was in Spain, near this corner here. I was there for a conference, and I didn't really pay attention to the location of the place until after conference, where it was used to be considered as the end of the earth, where looking into the ocean is Atlantic Ocean, and it was once considered to be the end of the earth. And it was not long ago, the earth was considered as the center of the universe. So that was, I found that was very interesting and very interesting to look at back how it was not too long ago that was our view. And I'm trying to, by the end of the talk, I'm trying to give you some idea where we are now with that kind of view, where are we in this the universe, if you will. So I was started with how we get to today. Really, the main milestone, one of the major milestone, is the unification of gravity on Earth and in heaven. This is everybody knows this story. There's a falling apple. Newton realized by watching that and made the connection between the falling apple and the moon around the Earth, or the Earth around the sun. The way to think about this is you can do a thought experiment. Think about if you play golf, you hit a golf ball and it will fly for distance, will fall down because gravity will pull it back to Earth. But if you keep doing this, and if you hit it harder and harder, it will get further and further. At some point, it will just it goes around the Earth and does not fall down anymore. And in fact, it could even come back from the other direction and hit your head. So this is something what I would call the end of the Earth is actually endless. And this is, of course, people realized this much earlier, but it was Newton to really mathematically, solve all this and made the whole thing coherent, and realized that this gravity on Earth is actually the same as the gravity the moon is experiencing. So that was the base of Newton's law of physics, and he even invented the calculus, which is amazing, to predict the motion of all the planets around us. And it was done a fantastic job predicting everything really accurately, except Mercury, and which I'll come back later. The Mercury is a special one because it's the closest one to the sun, and that was the entire classical physics, Newtonian physics. Mercury was a little bizarre. That was later on solved by Einstein by introducing general relativity, but that was an interesting story later on. The point I want to make is back then, England was the center of this scientific development, and it was no surprise that the Industrial Revolution actually happened in England back then. So that it was something to be noticed, because later on, as we'll show you, it will move to US. Over the 100 years later, it started moving to the US, and later on we'll show you a lot of scientific discoveries and technological development is actually happening in the US. But it has a lot to do with the scientific culture and the society, the support of this scientific research. So let me move on to the next slide. Hold on. So the next one is another level of unification happened between electricity, such as lightning, and the magnetism. The magnet, and those things look totally different. And also the lights, light bulbs, what we usually experience by looking at things. And turns out they are all the same thing, this is astonishing and very shocking at the time when people realized this. And this was realized, unified by Maxwell, which is a US physicist. And mathematically, he came up with Maxwell theory and to unify all those very different phenomena and proven that they are actually the same thing. And the electrical and the magnetic waves actually travel at the speed of light as well. So that was a huge success in modern physics. And if you look at this whole thing, what that enabled us is that for humans, the visible light is actually a very tiny window in the wide spectrum of electromagnetic spectrum. And the visible light is just part of that. And all that means is the visible light is the exact same electromagnetic waves, except with a very narrow frequency window or wavelength, if you will. And its wavelength is on the order of a bacteria, and it's bigger than, its wavelength longer than virus, so that you cannot see virus with your naked eye. But on the left side is infrared, as you move up, and then microwaves, and then this is where radar was really developed. And radar development, as you all know, it was during World War II. And later on, after World War II, the radar technology was all that processing, all that knowledge, all that industrialization of the radar machinery to make more radars. Back then, after World War II, it was turned into something like making microwave ovens. So that was found practical use for normal times. And later on, I come back to GPS as well. It was using those kind of frequency or microwave range frequency to communicate. Then towards left is the FM radio and AM radio you all know aware of. But the wavelengths get longer and longer, to the point where it's bigger than the house, so it can go around the house and all that. On the right side is much harder ones, what we call higher energy ones, from ultraviolets and to soft X-rays to gamma rays. The ultraviolet is actually very unique that it is the first window for humans to realize the quantum world, quantum physics, because ultraviolet energy is actually just about high enough to lock electrons out of the orbit of inside atoms. So that was the very first time that humans get the sense of there's something going on in the small world where the quantum physics was started based by those kind of observations. And this phenomenal success of Maxwell's theory requires one thing. It means that there has to be an absolute frame of reference based on Maxwell's theory. And that means there's there's the Easter, what we call it, filled up the space. And people searched for it for a long time and could not find any of it. And that leads to Einstein come up with special relativity. Essentially says there's no absolute frame of reference. Any reference is good. And the speed of light is always the same, no matter how you measure it and how fast you travel. So that is a huge advancement in terms of understanding. And I will come back to this. Later on, everything we do at Fermilab is all about relativity. Everything is for us. This is like daily life type of thing we use. So keep going. The next big advancement for humans to understand in terms of what is going on around us is the unification of space and time. And this is much, much beyond what Newton has done. What Newton was done is the unification of gravity on Earth and in heaven. But what Einstein realized is that the gravity is not really a force, it's more about the curvature in the space and time. And that is basically he's moving the special relativity into the general relativity. And this is a huge advance. And the first thing he solved the problem is the Mercury orbit, near the planet near the sun. Newton could not explain its odd behavior, but Einstein actually was able to recalculate and show that if you follow general relativity, it will work. But most people didn't believe in him because it was a known problem for a long, long time. And you can always come up with some theories to explain that away. So then Einstein made another really bold prediction, because his theory is that the curvature, the space and time around the Earth or Sun with a massive object, it's all curved, and even light has a bend around it. So that is a huge, big, bold claim. And here on the left, you can see the galaxy behind the sun. If you are on Earth, you're looking that way. He's claiming that the lights coming from the stars from the galaxy far away will reach Earth, and the sun will bend that light. And so that is a huge claim. Initially, nobody believed in him, but eventually somebody. But Einstein actually suggests a measurement. That measurement was also very nicely, it was a very nice idea, good idea. It's basically using solar eclipse. And you can see from the Earth, when the sun is covered by the moon shadow, essentially you can see the star in the background. And what you do is half a year before this happens, the Earth is on the other side of the sun, and you can map out the sky and match all the star locations. Then half a year later, when it rotated back to the other side of the sun, and when the moon is getting in between, then you can measure the same star, looking at the same star again to see if it's the same location or is put away from the original location. And he predict how much offset it's going to be, and that turns out in 1919. In 1916, people are already trying to find it, but World War I started, so people couldn't do it. But in 1919, people actually done this. This is in Brazil, and it's also Aruba, and all near somewhere in South America, and they actually really found out that it was really the star was offset by exact amount the amount Einstein predicted. So this was actually what made Einstein famous. Most people don't realize this, but this is actually made him an international hero, and people start because even though he got Nobel Prize for totally different things, not for something this big. But ever since then, it took a long time before people paid attention to this, because people thought that this is something happens in space, in heaven. It has nothing to do with what's on Earth. So nobody paid attention, but later on I'll come back to this point. It's actually something your daily life depend on this, which you can guess what that could be. So before I get to that practical aspect, I want to say something about a little bit more about how big this theory is. Mathematically, right after black hole general relativity come out, people can already calculate based on this is equation, which I will not show because it's a very complicated equation. You can predict there's a black holes exist, which is massive object. It was so massive that the gravitational things were dominating, and just nothing comes out of it. Anything gets close or sucked in and never come out. And also at the same time, it could predict the gravitational waves, which is just like you're throwing a stone in a pond, the water ripples will just going across the whole surface of the water. The same thing would happen if there's a massive amount of mass, such as two black holes colliding each other. I mean, this is what we're talking about, the black hole smasher here. And then it will generate huge gravitational waves, ripples, and it will go shock across the whole universe. And this was actually, people spent many, many years looking for this. I know 3 generations of physicists have been looking for this, and it was until 2015 they finally found it, and it was caused by 2 black holes crashing into each other sometime about 1.3 billion years ago. And you can really simulate this whole thing, and you can really look at the sound, in the time, the sound waves. So this is a huge success. And one of the professors got a Nobel Prize, Barry Barish, was actually my advisor's advisor, and I used to know him very well. He used to work on particle physics with atom smashers, but later on, sometimes in the 90s, when I was in graduate school, he started to get into this gravitational wave detection. So this probably was the most successful scientific achievement in the 21st century. I would say probably in the whole scientific history, this is really phenomenal, because you can really listen to what happened billions of years ago when 2 black holes, such a violent event happened, and you can actually listen to it. So now let's come back to the reality. So turns out the GPS you use every day, it has a lot to do with special relativity, and in particular general relativity. Because as I point out, based on general relativity, the Earth, because of the massive, the space and time is actually also curved. It doesn't curve as much as near a sun or near a black hole, of course, but nevertheless, it curved enough that if you do not do corrections to it, your GPS will never work. GPS can be off by many kilometers after a few minutes. So this was called gravitational time dilution and the dilation, and also special relativity. When a satellite travel fast enough, the clocks on that is running slower. So all those corrections have been made in order for this to happen. As you all know, GPS was originally started by military in the 60s, 70s, But it was in the 50s when one of the professors at Princeton, John Wheeler, really pushing people to pay more attention to general relativity. And someone proposed to test Einstein's general relativity on Earth by using satellites. But it turns out that test was an idea. If you turn it around, you can actually use that. If you believe in general relativity, you can use that satellite to determine the positions. So that was a very interesting history of how those purely curiosity-driven research, in the end, how it turns into something so useful and something we are so used to it now. You probably, many of us, me included, cannot really live without the GPS anymore. But the accuracy of that, it's all totally because of general relativity, and of course, I mean, as well as Einstein's special relativity. And I will point out not only those two, but quantum physics is also deeply involved in this, without which the GPS will never work. Because it was quantum physics, which I'll come back later to this, that enabled the atomic clock. And the normal clock you have in your cell phone or in your car, those clocks will never have that accuracy to allow you to determine things down to this level, because speed travels so fast that you know, if you're off by nanoseconds, you're already off by many centimeters. But if you're off by milliseconds, you're just totally. If you're off by microseconds, you're off by a lot already. So this is something to keep in mind. I will not go into details of this. By itself, it's a fascinating topic as well. But actually, my daughter is doing a science project. She's 12, and I got her to study the performance of iPhone GPS under different environments. So we'll see how that goes. But it's something you can learn a lot about fundamental physics, because all the modern physics all showed up in the little device such as GPS, what you have in your hand. So next, let me go to another level, which is getting into the quantum world, and the periodic table everybody knows. But you know, it took me even many years to really start to appreciate how much you can actually learn from this. This took many years, of course, accumulation, but it was quantum physics made sense of all this, what actually happening here at all levels. So the things I want to point out here is, one thing I want to point out here is there's this different color here. And the yellow color is what we call non-metal, and the green is we call metal. In between, there's this little tiny zone here, we call it semi-metal or semiconductor. And this actually made a huge difference in our modern lives. And I will use that as an example before I get to other examples of science. But before we get there, let's just point out that the age of quantum physics. It was quantum physics made sense of all the stable, why they behave this way. It has a lot to do with how electrons orbiting around the nucleus, and how many electrons are they, depending on how many protons, which is positively charged in the nucleus. And it depends on how many protons you have, that determines which elements that is. You can see the hydrogen has one proton inside, positively charged, and has one electron orbiting around it. So I have only one electron. But for other ones, you can see this B has 3 protons inside and the 3 electrons outside, but the 2 electrons fill the first orbit, and it fills the first orbit completely, leaving 1 electron dangling on the outer orbit. That is the reason why in this group 1, all these guys behave very similarly. But hydrogen, of course, is a very unique one because it's so simple. But the rest is all because there's only 1 electron in the outer orbit. So they all behave the same way. And later on, I will show you the semiconductor is similar, but has 4 electrons in the orbit. And all those things are explained by quantum physics in great details and tested in great details. And here is a picture I want to come back to later on. Just look at the simplest thing, hydrogen, where it has 3 isotopes. The isotope is just the same hydrogen, but with a little bit more neutrons next to the proton. So you still have 1 electron goes around it. And this is deuterium, this is tritium. And those 2 can merge together if they are getting too close to each other. And they can fuse into a helium. And it turns out, later on I'll come back to this, that was what's burning in the sun. What's burning in the sun is the this hydrogen is getting too close to each other and then become helium, and in the process they release the energy. It actually, by the way, it is actually how hydrogen bomb works. So this is again based on those understanding, all those things humans are able to understand. But one thing I want to point out is based on quantum physics, this orbit of the electrons has different orbit, and they have excited states with higher energy, and they can jump between those energy levels, and in doing so, they will emit a photon or electromagnetic waves with very well-defined frequency, because the energy is so well-defined, and that is so good that that's how atomic bomb, atomic clock is going to based upon, is because this frequency is so well determined, so precise that you can actually determine, use this to build a clock. It's really extremely precise. And I will come back to this point later. So let's use semiconductor as an example. The semiconductor is unique in a sense that, for example, use silicon as an example. You can see silicon has 14 protons inside, so there's 14 electrons around it, but it fills inner orbits up, and then outermost one only have 4 electrons left. And because of that, they can form a lattice. They can bond to each other by sharing 2 electrons with each other. And this actually turns out to be a very interesting property people come up to make use of it. Is on the right side, it's actually a different way of looking at it. You look at the 4 electrons and the 4 protons, positive charged particles inside. If you only look at this, you can see they bond together nicely, and everybody's charge neutral. Everybody has its location, and everybody's comfortable in here and all locked with each other. But if you put some doping or some just contamination into it, like for example, you put another particle atom which need a bit more charge, one more charge here, and you will end up a lattice, a structure where there's 1 electron dangling around, and that electron can move around, and that is how semiconductor really come to existence. And that's how, when humans find out this, and that's, gee, we can make use of this. And this, what happened was, this all happened in US, by the way. This is the first transistor that it was invention. It was based on this property. This actually using germanium instead of silicon. This was in 1947. Very first transistor. This huge big piece, right? Big piece, and this 3 of them got Nobel Prize in 1956 because of this discovery or invention, if you will. And pretty quickly, people started building transistor radios, and I'm sure you all heard of. There's also a few transistor computers, but nobody knows back then. And then there's also something called MOSFET invented at Bell Lab. It's different ways of doing transistors. But I will not go into details of that, but again, this is the Bell Lab. This has all happened at Bell Lab, by the way. Then one fundamental thing which people probably do not realize is the integrated circuit, which is able to make a chip, was invented at the time based on, motivated by all those transistors. And they can put all these transistors together, making a circuitry which is all integrated into one piece. And that was very hard to do and very, very costly. But luckily, at that time, the very first customer was actually Air Force and NASA Apollo program. They have deep pocket. They have eventually, basically, hundreds of $1 million went into it at that time. That is equivalent to a lot of $1 billion today. And because they wanted to have those individual components integrated into one circuit for launch into space, because that's much more reliable. Because if you have individual components and soldered together, when you launch and all that checking, all that harsh environment in the space won't work. So this was a huge interesting thing. It's just like a radar. Radar technology would never get to this point without World War II, where military really put a lot of money, gave it a huge boost. And later on, when the war was over, this actually, once it get to commercialization of it, it became so much cheaper that everybody can afford a microwave. if there was no military support with deep pocket, those things cannot become reality. The same thing with integrated circuit. Without this phase, interesting phase during the Cold War with the Apollo program, the manufacture of those chips is enormously expensive, and nobody can afford to have any pocket, calculator or personal computers. So I just wanted to point out this because most people, me included, it took me many years to realize that interesting history there. And this actually happened many times in the history of science. When the scientific become turned into technology, it always goes through some of this kind of those phases. So just keep that in mind. The rest, of course, is history. And I just want to point out that modern chip, like the ones you can find in your computer or your cell phone, can have billions of transistors inside. And because they're so tiny now, because of the integrated circuits, that's a huge, huge advancement for turning those scientific understanding into commercially available devices, which we now all depend on. So this fundamentally, don't forget that fundamentally is the understanding of the atoms and the quantum mechanics. To understand the atom, the behavior of it. Once you understand the behavior, you can manipulate it. You can put one different kind of atom and stick them inside and doping it, what we call, and then you can change the whole behavior of it. So that is still because of fundamental understanding of at the atomic level. So the next thing I mentioned before is the atomic clock. This is really the ones based the standard we use now is cesium, which is a much heavier nucleus, but it has this special states where the transition has a very well-defined microwave signals come out, and you can use that to count per second how many is about 9.19 billion oscillations of this electromagnetic wave coming out, and you can use that to build a clock, which now achieved 10 to minus 9 seconds per day accuracy. That's nanoseconds. 10 to minus 9 seconds is a nanoseconds, what we call. And what does that mean? That it means is really, I can give you, put things in perspective. Long time ago, hundreds of years ago, in England, when Royal Navy lost the entire fleet because they couldn't determine longitude well on the ocean. And they really put down a lot of money, equivalent to probably tens of millions of dollars today, to avoid anybody who can come up with a solution to solve the longitude problem, to determine on the ocean, not on land. And major smart genius like Newton and Galileo all spent many years doing this. And they are trying to use what's going on in the face of the moon, the satellite for Jupiter to determine those things. But on the ocean, it's very hard to look at the telescope looking at the satellite of Jupiter. So that was not practical. But in the end, it was John Harrison, an 18th century clockmaker, who built a mechanical clock, the very first one, sufficiently accurate enough with the accuracy of a few seconds per day. And that solved the problem. And then he got the prize, he started when he was a teenager, in fact, but he got a prize at the age of 80. That was really a fascinating story. The book Longitude is something I definitely would recommend if you read it if you haven't done so. But that was based on a genius who was so good at clock making and mechanics and all that stuff, and achieved a few seconds per day accuracy. But it was scientific understanding of fundamental, at atomic level, fundamental understanding with quantum mechanics and all that, to enable us to reach the 10 to the minus 9 seconds per day. This is only a couple hundred years later. That is equivalent to a few seconds of over 100 million years. Okay, that just gives you some idea how much humans has achieved to this day in terms of clocking. So I will not have time to go into this. There's a lot of more we can talk about it here, but I will try to be brief here. Another one I want to point out is look at the atoms. Everybody likes gold. For 1,000 years, people trying to turn mercury or lead into gold. but they have no idea why they are similar. Of course, they just empirically think they are similar, so they're trying to turn this into each other, and nobody actually was successful until today. With modern technology, with what we know in particle physics, we can actually turn mercury or lead into gold, but with two caveats. Number one is the amount of energy you take to build an accelerator and turn this into gold. The cost is much higher than the few gold atoms you'll end up with. That's number one. Number two, the gold atom you end up with is actually isotope of gold with extra neutrons in it, and they are radioactive, so you cannot really use those gold to put the ring on your finger or build a necklace out of it. So, but nevertheless, in modern times we do this all the time, but not on gold. We do this. This is actually goes back to Fermi, Engelbert Fermi, who's won Nobel Prize in 1938 based on his fundamental understanding of how those things works. We call it weak induction. This is what happened inside nuclear. And he's the first one who came up with theory we call it Fermi induction. In fact, like in grad school, we still taught this is Fermi induction. He came up with a way of using uranium-238 and shooting neutrons into it, and it will eventually become plutonium-239. And as you know, this is the most dangerous element on Earth because it can build bombs, but it also can turn into nuclear energy as well. But this is again the knowledge going to deeper level in terms of nuclear allowed us to discover those kind of amount of energy along the way. So this is, Fermi was considered as the father of the nuclear age. And now, so something what we do, I'm also running out some time here, is really what inside the proton and neutron. And that is the region where my specialty is. It is actually quarks and neutrons. And those are fundamentally building blocks, what we know today. And we are really spending a lot of years to study the fundamental behaviors of those quarks. And here, what's showing here, protons, what you stand here is up quark and D is down quark. The physicist does not have good way of naming names, so it's up and down. It's very simple. But later on, I'll show you there's much more quarks out there in nature, which we discovered. And along this way, they discovered another force, which is called strong force. Those strong forces are the ones bonding those quarks together, forming proton, and the proton then bond with neutron, forming atoms, and from nucleus. Nucleus bond with electron, forming atoms, and that's how we come to existence. So the strong force is something we don't talk about, we do not know, but it is really fundamentally made us possible. The very existence of us depends on the strong force. But those are the things we study. Weak force and strong force is what things we are studying. And the weak induction is actually responsible for all the radioactive decays of atoms, and plays an essential role in nuclear fission. And also it is pretty essential in the combustion of the sun. What's burning the sun is, I told you before, it was hydrogen fused into helium, and it was all due to the weak induction made it possible. And the force carrier of this boson, this weak interaction, is very similar to the photons as a carrier for electromagnetic forces. So the next level of unification in terms of human knowledge towards those things is the unification of the electromagnetism and the weak force. And what you talked Maxwell before, those photons, electricity, and the magnetism is actually the same thing as the weak interaction, which we know. And it turns out that we call it electroweak theory. And that was done at Harvard. Two professors I used to take class with, and they and plus one from Salam from London, and this discovery of WZ boson, because they predicted WZ, and discovery of boson was by Carl Ruppia, was also a professor at Harvard at that time. When he first heard about this WZ, he first come to Fermilab trying to convince the Fermilab director to change the accelerator to do this, but the Fermilab director told him to get lost. It was a very interesting story. And he was so he was so mad, and then he went to CERN in Europe, and Europe let him do it, and then that was discovered in 1983. So there's quite a bit interesting history behind this. I will not have time to get into, but now this is the big picture. You can see that the atom is the size of 10 to the minus 8 centimeter. Then the nucleus is 10 to the minus 12. The electron is tiny, but it occupies all the empty space because it travels really fast and spinning around. Then proton is 10 to the minus 13 centimeter, and the quark is at 10 to the minus 16 centimeter. This is what we are studying with our accelerators or atom smashers. So now finally, I can say a few words about atom smasher, but I will be very brief. You can smash many things at each other. You can have electrons, positrons, which is the antimatter of the electron, or protons, antiprotons, or proton-protons, or even heavy ions, as I said before, lead or gold ions. And or even that's also muons, which is a cousin of the electron, but does not live too long. You can build a muon collider as well. And I've worked on quite a few, 5 or 6 of them in the past. And the way you find, there are many other quarks actually based on the theory, this unification of all the theory predicts many other things. And there's, besides up-down quark, there's also charm, strange, top, bottom. You can see the name of this is all had historical reasons why they named it this way. The strangest was the first one discovered, and they found it very strange. People didn't think that it was possible. But then very soon they said, if strange exists, there must be something else exists, and then indeed it happened. So that it was charming. So that's why they named charm. But it was, and then there's beauty, then there's top. So it was very interesting history there, which I will not have time to go into. But the important thing to realize is those quarks will form the hadrons, and those barons, the protons, one of barons or neutrons, and then they in turn form atoms, nucleus atoms, and then atoms form molecules. So this is we are reaching the fundamental understanding of behavior of the quark level now, and that is very quite complete. And here it just shows the many colliders in the world, and I will just show a few recent ones. This is a Tevatron at Fermilab, and this was turned off about 10 some years ago. I worked on this for many years. This is actually colliding proton and antiproton together. Okay, this antiproton is the antimatter. So matter-antimatter collider, if you will. And this is the Large Hadron Collider at CERN, and it's actually a proton-proton collider because it's easier to make more protons. And the reason we had the proton-antiproton at the Fermilab is because it was cost too much to build 2 rings to host both protons. And if you use antimatter, you can use the same ring. They can travel because they are opposite each other. They travel in the same ring in opposite direction. So that was just really to save money. But for Large Hadron Collider, it was a proton-proton collider, and that's much bigger ring here. And also at the same time, the same collider can used for heavy ion collision as well, because the ions will be charged, you can accelerate them as well. So, but the proton-proton antiproton collider is actually also good from physics point of view because it's purely symmetric collision, and that is actually has some advantage as well. So here's just some pictures of those collider. The collider, you can see Geneva is over here, Lake of Geneva is over there, and the Geneva cities are over there. And there's a couple of collision points where the protons will be brought, and proton beam will brought together, and they will have a very violent collision. And the whole thing is 27 kilometers. And those around the picture here are the detectors. I'm working on a CMS detector. And I was working on ATLAS for a brief time with the University of Chicago. And also detects what's coming out, the debris of the collision, violent collision here. And this shows the raw information from the detector come out when you're looking for something. You have to really looking them with a higher and higher intensity in order to produce them. And this just shows a different intensity, what's coming out, what you're looking for, and what it's actually buried inside a lot of other junk, and you have to sort this out. And that it takes a lot of data processing online in real time, And that's the important thing here is to realize it's intensity is very, very important called luminosity. And this is I will use a old story I learned from my graduate school days. My experiment was at Cornell, so I had a chance to meet Hans Bethe, and he's the one figured out how the sun, what's burning in the sun. Okay, he got Nobel Prize in '67. And the one physicist could not find a girlfriend for a long time, and very frustrated, he complained to Hans Bethe. And Hans Bethe has used the language that the student understand. Basically says, young man, if the cross-section is so low, increase luminosity. The same is true for searching for new particles in our field. Is in order to find those exotic particles, collisions, you have to really increase the intensity of the collision and the luminosity of the accelerator. So this is actually a picture showing what you're searching for is up here. That's a collision, collision with 4 muons come out, particle come out. This is a heavy Higgs searching for a particle, which is a new physics with a heavier Higgs. And this is what's going to happen in the near future. In a few years from now, we are upgrading the LHC, and which I'm deeply involved, to make the collision happen like this. And from this kind of collision, you're trying to find some new particles. This is finding a needle in the haystack, as much as this collision happens essentially billions of times per second. Happens. So, and you have to sort this out without any software. Online, you have to sort out in real time which event to save, and then you can offline. You can do a lot of computing. You need a massive amount of computing power to do. This is as big data as it gets, and you have to process them and trying to looking for those particles. So, long story short, this is all the discoveries of what you call this is what the standard model of what we know today. Understanding the fundamental things at the quark level, and it predicts all those particles, and all those particles actually are found over the past couple of decades. You can see most of them are found at the U.S. on East Coast, West Coast, and Chicago, some people may say this is also highly correlated with the civilization, the location and where those things are discovered, and the same thing. The other particles are found at CERN. That it was in Geneva, Switzerland, and you can see the latest discovery is 2012. That's Higgs discovery. That is the most important fundamental building, the building stone, cornerstone of the standard model is the Higgs, and it was predicted. And people searched for 30-some years. Finally, in 2012, it was discovered. So before I move on, I wanted to say a few words about the real atom smasher, which is a heavy ion collider. The same accelerator, you can put the ionized heavy atoms like lead or gold into it, and you can accelerate them, you can smash them together. And this is smashing those together is no longer study quark level stuff. Well, rather by smashing together so hot, the temperature it can reach momentarily trillions of degrees of Fahrenheit. Okay, so everything melt into a quark-gluon plasma. The electrons all gone. It's just back to its basic, stuff, and then it will cool down instantly because after the collision. So this allows you to study things what happened in the early universe. And here's actually event display. You can see how violent this is, how much stuff coming out of it through that collision, that smash into each other. And when this whole thing momentarily become a quark-gluon plasma, and how much energy inside, and then immediately it will cool down and they become real particles such as quarks and such as protons and neutrons. And the protons will search for electrons to combine. And if they combine together, it will become a hydrogen atom. So that's how the universe was started in the early stages. Is the eventually after quark-gluon plasma, they will become nuclear matter. Nuclear matter then become protons, neutrons. Then neutron will bond and then looking for electrons, then become hydrogen. Once hydrogen gas is formed, and then the gravity will take over slowly, and then the hydrogen will get together really close. When they get really close, the hydrogen will fuse together, become helium. Then it will then become burning of the star, which is what happened in the sun. So before I will just quickly, US was trying to build a huge super collider back in the 90s, but it was canceled in 93, and that's why CERN Europe took lead of this. this machine was much bigger than what Europe has now, but it was terminated in '93. So that was a big thing for U.S. scientific research, big step backwards. But there's other big machines proposing here in US. There's no official proposed machine. It just shows you the big machine we call a very large hadron collider is going to be this size, where Fermilab right now is this size. Okay, but in Europe they are talking about building a future circular collider which is 100 kilometers long. This is still a proposal, and this costs quite a lot of money. So this is still just at the proposal stage, and people are doing studies on this. So before I move on, I wanted to just getting back to this very quickly, spend a few minutes. So what's burning in the sun? With all our understanding at this level now, we now have total understanding of what's going on in the sun. It's really nothing but the hydrogen, which I told you after quark-gluon plasma, they form nuclear matters, and then protons. Protons were looking for electrons that become hydrogen. Hydrogen will be pulled all together by gravity, and then they will, when they get too close to each other, the gravitational thing pushing them close to each other, they will fuse into helium, and by doing so, they actually release energy, and that's what you see. That's what we see. The sunshine. It's all due to that process. And as you can see, of course, the other aspect, downside of this is, of course, the hydrogen atom is also based on exactly the same principle. But on the other hand, one could turn this into something for human, for society, which is, this leads to the most ambitious energy project in the world, is trying to emulate in the sun. It's a deuterium nuclear fusion reactor. This is a huge project, which took us more than 30 some years to finish. It's called ITER. I just want to mention this so that in case you're not aware, this research is actually going on. Of course, it's going on in the past 50, 60 years, in fact. But the most recent one is the major one is actually the international agreement that was reached in 2006, and finally picked the site at southern France. US, of course, is a major player in this, but initial operation will be not until 5 years later, initial operation. But the real fusion reactor operation is actually not until 2035. But keep in mind, this would be the cleanest nuclear energy without any other contaminations, because deuterium can be got out from seawater, and this is also very natural because that's what's burning in the sun, and there's no nuclear waste left behind. So that's why people are so into this. And another thing I want to point out is, based on our understanding, we understand how all the stars actually form and how they die. Our sun is very small, so that's why it's only helium, hydrogen burning to helium, that's it. But for much more massive stars, like 20 solar mass stars or bigger, they were going through a process, and they collapsed until they become iron, and the iron was formed. And at that point, they cannot collapse anymore. They cannot collapse anymore to fuse anymore to release energy. So in the end, what will happen is the gravity will take over, and then the whole thing will collapse, can no longer hold itself because there's so much pressure inside. That is what we call the supernovae explosion. And this has been observed, of course, many times in the history of human history, but it's only in the recent decades we started to have a deeper understanding of what actually happened. It was due to this process and within 1 second of this explosion, all the rest of elements are made in the universe. And so including the gold that people like, gold was only made after a massive star exploded into supernovae, and that's so violent that all the elements have been made. So in many ways, if you think about it, we are actually made by dust, but it's not any dust, it's stardust. And those stardust has gone through dramatic development into a supernovae in order to make those stars. So that's something to keep in mind as well. So this is based on our understanding now. You can see this is our understanding now is there's a Big Bang, but we cannot directly prove it, but we can indirectly, all the observations consistent with having a Big Bang in the beginning. And then there are things forming the nucleus, the quark-gluon plasma will form. And this is where the experiment we're doing with different accelerators and with proton collides, this is where probing the phenomena near
Big Bang, but not quite in the Big Bang. And then there's heavy ion collisions who are probing the quark-gluon plasma, and so on and so forth. So, and then we're living here today. But we have probed, by using atom smashers, we have probed all the way close to the, very close to it, within, I would say, within microseconds of the, right after the Big Bang. That's what we're probing right now. So this is where we are in terms of scientific capability and how much humans have advanced in this direction. This is going back to the basics again, the curiosity-driven research. What curiosity-driven research has led us to, from very beginning, I told you the electricity mechanism lights that become unified into electrical mechanism. Then weak nuclear force discovered, then was unified into electrical weak. And then strong forces discovered. And then this thing become the standard model of particle physics. And the standard model is totally proven experimentally as of 2012, the year 2012. So the next thing we still do not know, and we're still at lost. The same thing on this side, initially is gravity on Earth and in heaven unified, but then Einstein pointed out it's really just space and time, and that's become general relativity. But then is there going to be a quantum gravity? We still do not know the answer to that. And is that going to be ultimate theory of everything? We do not know that. So this is where we are in terms of fundamentally just curiosity driven, how far it gets us. So now it's back to what we had before. Now you can see, hopefully by now you look at this cartoon, you will have a different way of looking at this whole adventure of human curiosity driven research. So, and I will end my talk back to the picture, what we call the end of known world. Even though what I talk about, all the things so far, all the things we talked about is actually about the atoms. And based on our current understanding, all this observation, cosmological understanding, it's actually 4% of universes was considered with atoms. We are made of atoms, of course, but there are still a lot of things we call dark matter, dark energy, we do not quite understand. Still out there. And if you look beyond this, we're still in the dark. But there's still a lot of experiments searching for dark matter and dark energy. Will not get time to get into, but I would just call it, this is today's end of the new world. So I hope I didn't run over time too much. That's all I have today.
Thank you so much, Ted. And I can only hope that our government continues to, or starts to fund science more and more, so that who knows what technology we'll have and life improvements because of it. Does anyone have any questions for Dr. Liu? You can either type them in the chat, or you can unmute yourself. Okay. Well, we've reached the end of the hour, so thank you so much, Dr. Liu, for speaking to us today and telling us about all that's going on in the quantum physics world. I know it's a lot, and there's so much more to learn. Thanks for getting a taste of it.
Yeah, this is a huge topic. As I said, I can only have to be very highly selective and highlight what has happened in the past couple hundred years. So there's so much. So it's such a there's so much out there to talk about.
Okay.
But hopefully it's not too much for people to. I hope hopefully people can actually understand some of what I said.
Yeah. Thank you very much.
Thank you, everyone. Have a great evening.
Thank you.